All right, and welcome to General Relativity in Geometric Algebra 6. And we're just continuing the polar coordinates example. So this is the second video for that. We'll, in this video, calculate the connection bivectors and then the curvature multivectors from this. And these are what you use for Einstein's equation. So first, just recall the derived formula for the connection bivectors. So that is recall that the bivector with a beta index, and this is defined as this is equal to 1/2 G alpha wedge partial beta G alpha, then plus G epsilon wedge partial G beta epsilon. So this is the formula for calculating the connection bivectors. Now remember that we showed in the last video that the metric was diagonal. So remember that the metric is diagonal, meaning that G alpha beta is equal to G alpha alpha, which implies that G alpha is proportional to G lower alpha. And if you're not convinced by this, remember that in the last video, we had an identity somewhere in here for that. Where is yeah, we have it right here, that they are indeed proportional to each other. So if they're proportional, then this wedge product should go to 0. This should vanish. So in reality, the calculation is much simpler. It's 1/2 G epsilon wedge partial G beta epsilon, except because it's diagonal again, all the epsilons that aren't beta will disappear. They'll go to 0. So in reality, this is just G beta wedge partial G beta beta. Now, therefore, the calculations are easy to perform. For t, it's 1/2, and then we have gt wedge, the partial of a constant. So this is 0, and likewise for omega r, we have 1/2 gr wedge, the derivative of a constant -1. So this is also 0. And then omega theta, we do a better theta, 1/2 g theta wedge partial, and then g theta theta is just r, or actually it's minus r squared. And that is just going to give us minus r g theta wedge g gr. And then recall, so in tetrads, we have that z theta is equal to 1 over r, or gamma 2. And that zr is just equal to this, and we'll also have this identity, which we'll use in a second. So we have these identities for the tetrads, and these are the ones I encouraged you to calculate in the last video, because they're just you end up with just reciprocals of the the coordinate basis. Okay. Oh, and then we want to put this into the coordinate basis, so that's going to be minus. So plugging both of these in, we cancel out the r, and we just get minus g21, which is just going to be, or a gamma 1, 2. Okay, so we have that. And then for omega phi, we have 1/2 g phi wedge partial of r, or minus r squared sine squared theta. So it's just going to give us minus r sine squared theta g phi wedge gr plus, or rather minus, r squared sine cosine theta sine theta, and then g phi wedge g theta, which when we simplify this thing, plugging these in, then for this one, we get sine theta tetrad 1, 3, and then plus cosine theta tetrad 2, 3. So now we have the connection bivectors. We have 0, we have 0, 0, gamma 1, 2, sine theta gamma 1, 3, cosine theta gamma 2, 3. Okay, so let us then move on to, let us now move on to calculating the Riemann bivectors. We'll now calculate the Riemann bivectors using the following formula. R alpha beta is equal to, or just so that we can recall, it's G alpha wedge G theta equals R alpha beta partial alpha omega beta minus partial beta omega alpha plus the commutator of these two. So automatically, for every possible coordinate basis, it's true that R alpha alpha is equal to 0 for all alpha. And that's just saying that you can't have curvature, like if you're considering only a single direction, you can't have curvature in there because where are you curving into? So that's like saying like time can't perceive itself being curved. You have to have reference to the other dimensions. So that's why you only consider off diagonal terms because the diagonal goes to 0. So let's now calculate the Riemann bivectors. So therefore, we just know automatically that RT and then for any alpha equals 0 for all alpha, just because this, and we know that every bivector, we know that every connection bivector doesn't depend on time. So if we take the time derivative of it, it goes to 0. And then the connection bivector for time is also 0, which means that these two things vanish. So for all indices, the time-like Riemann bivectors vanish. And then R, the first one that isn't super trivial, is R theta. So we get partial R minus 4, and then plus these. And we know that these vanish right away because omega R is 0. So we end up with partial R of 1 over R, 1 over R, we call it G R wedge G theta. And this ends up being 1 over R squared minus, and then it's partial R of G R wedge G theta minus, and actually it's going to be like this, plus G R wedge partial R G theta. So we can simplify that, or we can just use the tetrad, which is this, and it's 0. Likewise, if you plug this in, you'd see that this would be 0 as well. So this term would vanish. And then if you take the derivative of this with respect to R, then this becomes parallel to this, so this vanishes as well. So you would see that this would vanish too. But this is just evidence for why we can use the tetrad. So for the rest of the calculations, I will use the tetrads. So then we also have R phi, and that's going to be partial R omega phi, and the other terms disappear for the exact same reason that they disappear here. So we have that, and that's just going to be dr using the tetrad sine theta gamma r13 plus cosine theta, yeah, tetrad 2, 3, and this is just 0. So then the last bivector we have to consider is r theta phi. And this one is actually the most difficult one to calculate because none of the terms just disappear. So we have to calculate every single one. Like so. Then we get d theta of this, then minus d phi of, or actually, wait, hang on. This term does vanish because this doesn't depend on phi at all. So this goes to 0. then plus, we have this, the commutator of these two objects. And so we end up with cosine theta, gamma bar 1, 3, minus sine theta, gamma bar 2, 3, plus sine theta, gamma bar 1, 2, gamma bar 1, 3, and then let's move everything. Let's move everything over. This plus cosine theta, gamma 1, 2 bar, gamma bar 2, 3. And this ends up giving cosine theta, gamma bar 1, 3, minus sine theta, gamma bar 2, 3, plus sine theta, gamma bar 2, 3, minus cosine theta, gamma bar 1, 3, which is, of course, equal to 0. And this implies then that all the connection bivectors are equal to 0 for all alpha and beta. And this should make sense. Polar coordinates describe flat spacetime. And so obviously this means that if it's flat, then all of the curvature goes to 0. And because the Riemann bivectors are all 0, that means that the Ricci vectors, the Ricci scalar, everything like that is 0. And so you can't have any curvature. But this shows how to actually do all of the different calculations. You have curvature, and things change. You can also have coordinate metrics that don't describe flat spacetime. So you wouldn't end up with 0 terms here, obviously, but all of the calculations are the same. And so I feel like it's best to just show a simple example